Okay, hello everyone to today's seminar on interval methods in control engineering. And it's my great pleasure to welcome David Sanders today. And before David will start with his presentation, let me give a brief overview of his biography. David has been a full professor at the School of Sciences at the National University of Mexico since 2008. And a visiting professor at the MIT during the period from 2019 to 2021. And just recently, he started with working with RelationalAI. I think there's a company situated in Boston where David is at the moment. And now I'm handing over the microphone to David, and we're looking forward to his talk on global optimization and interval constraint programming. The floor is yours, David.
Well, many thanks, Andreas, for the invitation to give a talk at this very nice seminar series. As Andreas said, I'd like to talk about some work that I've been doing over the last, few years really, on tooling, on developing nice usable tooling for interval methods, in particular constraint programming, and applying that to global optimization. And so the tooling that we've been developing in collaboration with actually many people now has been based on the Julia programming language, which I'll show a bit. And these are the topics that I sort of like to highlight today, how we can use symbolics and code generation to do constraint programming in a nice way, and hopefully attack the problem of how to do all of this on GPUs. So I'm going to try and give live demonstrations, and of course, live demonstrations always go wrong, and in particular, the GPU demonstration is not working right now, but okay. So yeah, this is work that a lot of it's been done in collaboration with Alan Edelman and his group in the Julia lab at MIT. So this is where the Julia language was originally developed and is still being actively developed by that group. And I'm not a computer scientist by training, but it turns out that a lot of the questions that come up in these kind of areas have to do with computer science, and I learned a lot by being around people who working in kind of from a computer science angle on, let's say, programming language design in that lab. Okay, so let me try and well, that doesn't, where is my, struggling with my Windows. Well, oh dear. I'm supposed to have a little arrow and it's just not appearing. So we'll sort of get that idea. Okay, so basically I'd like to talk about constraint satisfaction problems and how we can specify constraint optimization problems in a nice way within a language. I'll show our interval arithmetic packages in Julia, which was developed together with my colleague Louise Bennett at UNAM. And as I said, I'll talk about a code generation approach to constraint programming. And so just a word about Julia. It's a very nice modern programming language designed from the start specifically with the goal of scientific computing in mind. And so when we're developing something as scientists, we really want to be able to do that interactively from a REPL, in other words, a command line, or some notebook kind of interface. And we're coming from a sort of mathematical side, we want to be able to use mathematical syntax within that language. And so the point of Julia, the original idea of Julia, was that we want to be able to do everything interactively, but we also, of course, want it to be as fast as possible. And so the only way to get speed is with compilation. So Julia is a compiled language, and for some reason, many people don't realize this, but yeah, Julia is compiled. It doesn't feel like it, but it is. And that's how it's able to get speed, of course. So we can, but that's the point. It combines the sort of interactive style that you might be familiar with from Python or MATLAB with the speed that comes from compilation And so it has a similar speed to C++ or Fortran. And so in that sense, it solves the two-language problem where you might want to develop a prototype in Python because it's easy to write, and then you end up having to rewrite your entire code base in C++ because you want speed. And so Julia and our suite of packages are all open source, and we have a liberal MIT license. So we actually suffered when writing all of these packages from the fact that, of course, there are many interval arithmetic packages out there, great libraries, but the problem is that they don't have a suitable license. So many of them are GPL or LGPL. And so we often in the Julia community, people like this MIT license. And so we're basically unable to reuse any code from those libraries. And so we had to sort of write everything from scratch. And Julia has a large ecosystem of packages from all different kinds of direction. In particular, I'll show various visualization libraries. And so the point is that we can interface with those libraries to avoid having to rewrite our own. So for example, also forward mode automatic differentiation that we might need is already written. So again, we don't have to rewrite that. Okay, so let's talk about constraint satisfaction problems. So I'm going to actually, rather than just talk about it, let's actually show that. So here's a little GUI which you can hopefully see, where I can select an expression and modify it, and then I have some variables that I can change the value of with these sliders. And then here is the output of an interval constraint programming calculation of characterizing the set that satisfies this constraint. So for example, so let's choose something more interesting, something like this famous example by Tupper. So you can see that I'm specifying a symbolic expression, which I can actually modify. And then this is the exact symbolic expression that's being evaluated. And here is a visualization of the set that satisfies that inequality. So blue boxes are guaranteed to be inside the set, the constraint set, the relation satisfied by this inequality. White is guaranteed to be outside, and red is on the boundary. And so let's remove those boxes, and then I can start modifying these parameters. It takes a little while to recompute, and then we see a different, okay, that didn't seem to change much. Oh yeah, I forgot to actually add the parameter in here. So once I add the parameter, everything automatically updates. So this is the Pluto notebook, which is unique to Julia. And it's very easy. You can see the code to write these sliders is just sort of a piece of Julia code that is wrapped into a string, and you can hide it, and you get this nice interactive visualization. So I just, again, change that value, and the graph takes a little while because it's doing this whole constraint programming calculation. So it's basically bisecting these boxes. So I can change the size of the boxes. And as I change the size of the boxes, you can see the, hopefully, the standard kind of updating of the picture as everything gets refined more and more precisely. So that's the kind of thing we want to aim at. So how can we actually do that? And then, as I said, the final goal. So this is all running on the CPU. The final goal would be to run this whole calculation on the GPU. So I'll talk about GPUs for people who don't know about them. The graphics processing unit. Okay, so how can we actually specify a constraint satisfaction problem? So as you saw, what I did just now was had some kind of symbolic specification of this constraint programming problem within Julia. So often previous tools, you had to write the problem in some sort of domain-specific language that, something like AMPL or GAMS for constraint satisfaction, for optimization problems. So these days, we can actually do all of that from within the language in various different ways. So the way I've chosen to do it is with Symbolic approach. So this is a package in Julia, symbolics.jl, which allows us to define symbolic variables. So if I define variables like this with the add variables, then I have literally symbolic variables. So I can write a symbolic expression and it returns a symbolic expression. So if I do x times x here, it will simplify that to x squared. So it's just a standard sort of symbolic library, but it's actually very fast. Also, the author's claim. This is not my package. It was developed at the Julia lab while I was there, basically. And so how can I then use this? Well, here's an expression with this equals 0. So this is now a constraint in 3 dimensions. And so I just pass this to the constraint function from interval constraint programming. I'm passing in this symbolic expression, and it's doing the entire computation of what's called the forward-backward contractor for this expression. So I'll talk about that later. But the point is, it's starting from a symbolic expression that exists, it's just a standard object in Julia. And then I can define an interval box in 3 dimensions here. So there's 3 as 3 dimensions, and have an interval from -2 pi to 2 pi. And then I can pave this, I can run a paving algorithm on this constraint. So this is why here is the input box, and I called the constraint CSTRT, not a very nice name. So this particular tool that I'm using, you are unable to reuse names in different, this is Pluto, you're unable to reuse variable names in different parts of the script, which is why, or the notebook, which is why I'm using such a strange name. And this is the tolerance, the size of the boxes. And so you can see that the output is the set of boxes. Here we are, a set of interval boxes that cover this 3-dimensional surface. I actually wanted to be able to visualize that, but that's one of the things that's not working, unfortunately. So I can show you a different 3-dimensional visualization. And you can see that, this tool allows me to introspect, to really examine all of the output of these algorithms. But as I said, so what's happening here is that Julia is compiling, that's the key point. I'm actually compiling a contractor for this particular constraint and compiling all the way down to machine code. So it's as fast as it possibly can be to run this algorithm. Okay, so let me show you the output of something like this. So here's an example output. This is a tool called Maki, M-A-K-I-E. It's another Julia package for 3-dimensional visualization. And so this is a twisted cubic. So here's a quadratic, and here's a cubic surface. And the set of boxes are the intersection, which is a curve, one-dimensional manifold, one-dimensional curve in 3 dimensions, the twisted cubic, and I've just used very large boxes so you can see the output of the constraint programming algorithm. So these are, again, guaranteed to contain that 3-dimensional object. Okay. So let's switch to extend this to constraint optimization. So once we have constraints, then once we have the ability to compute with constraints using these contractors, then we can actually start talking about constraint optimization. So here's a very simple constraint optimization problem. And again, we're just writing this in Julia. So we're defining a constraint optimization problem object. We're passing in these symbolic variables that I already defined, x and y. And here, the objective function I want to optimize is x plus y. And then here's a set of constraints. I'm just using a vector in Julia. This is a vector of 2 constraints. And the input domain, written with a nice syntax with this Unicode operator, etc. So this is a very common idiom in Julia. I'm just going to define a new type to represent my problem, and then I'll define some kind of solve function that takes in objects of this type and produces the solution. So in this particular case, I'm just going to want to minimize this. So here's the feasible region defined by the intersection of these constraints, again, plotted using these separators, contractors that I've defined. And then we can solve the problem by calling the minimize function on this object with a tolerance, and we get an interval containing the global minimum and the set of boxes containing the set of minimizers, and we can, again, plot those. And here is the global minimum in this particular problem. And in a more complicated example, you might want to just set up everything ahead of time. So here, because we're using these symbolic objects, we can just define standard Julia variables. Variables. So here's a variable containing the set of symbolic variables that I want to use in my problem, P1 and P2. And here's the objective function defined as a standard Julia function. And now I'm going to pass in symbolic objects into that function to trace through to get a symbolic object out. So this objective is now just another one of these symbolic expressions. And once I pass these symbolic variables into my Julia function, I get out a symbolic expression that sort of represents the structure of that Julia expression. And then here's my interval box that I want to cover. This is an example by Hansen from Luc Jollin's book, or the book by Luc Jollin et al. So here's the set of constraints as symbolic objects. And then I pass all of that straight into this constrained optimization problem object to create the constrained optimization problem that I then minimize. And here are the clusters of boxes around the global minimum. So far, this is using a kind of more Skelbo type algorithm that I'll talk about later. And so far, it's difficult to actually refine this cluster of boxes, as we all know, people who work in this area. Okay, so how does this all work under the hood? So we have this interval arithmetic package, as I mentioned, interval arithmetic.jl. So it's very easy to use. So this is how you install from. So if I'm, from within Julia, you just do this sort of one-line command to install the package. So simply from within Julia, Julia has a built-in package manager to install the package that you do only once. And then to actually use the package, you would type using interval arithmetic, and that loads in the package in your current session. And then you can use this ... operator to create intervals. So for example, here's an interval containing pi, and then you can just use standard, we overload, just like in sort of your average interval arithmetic package, you overload all the operators so that we can write nice expressions like x squared plus 1. And we can do the same thing in higher dimensions using, as I said, this Cartesian product operator, which you write as \times, and then press the tab key, and it will basically, you can use these LaTeX abbreviations, so you can replace this \times, hopefully, with this Cartesian product operator, or there are, as I showed already, other ways to create these interval boxes in higher dimensions. So for example, here's an input function. Here's a function with which accepts a tuple of 2 values, and does some calculation, and then I pass in this interval box, which is basically a vector of 2 intervals or a tuple of 2 intervals, and I pass that into GGG, and I get back an interval that, of course, is guaranteed to contain the range of this function over this input set. And so, for example, you could ask, is 0 in that output, by doing 0 \in tab, and replaces it with this set membership symbol. And then I put in this output vector, and it tells me that 0 is not contained there. So, so we've designed interval arithmetic to be highly performant when you're using float64 intervals in particular, intervals containing float64s, which are, in other words, binary 64s with double precision, IEEE standard floating point numbers. Now you can also use big floats within interval arithmetic, so within the package. So for example, you could do z equals the interval from, well, let's say, so I already have this interval that I called, well, no, okay. So you could do big of 3.14. That gives me a big float version of 3.14. So as you can see, what it did was convert the float64 to a MPFR big float with 256 bits of precision by default. So instead of that, I can use this slightly strange, interesting non-standard string type to get a very close approximation to 3.14. Or what? Yeah. So now I'm getting confused. Anyway, basically, So what I really want to do is create the interval first and then convert it to a big interval. So this is now an interval of big floats. You can see that the precision is 256. So if I call this sort of my pi, then I can do operations with my pi just as easily as, I could put GGG of my pi, and now I get all of the calculations done in using MPFR in high precision with correct rounding, etc. So the rounding, directed rounding is an issue in interval arithmetic, a very important key issue. And so there are various modes of directed rounding that you can use within the package. And the fastest one is just to use, if you have some floating point number, you can do a pre-float will give you the previous floating point number. So previous float 64 in this particular case. And one of the modes of rounding in the package is to just use pre-float and next float to do all of the rounding at every step in every computation. And that's going to be the fastest and most GPU-friendly method of doing directed rounding. Okay. So let's go back to the constraint satisfaction problem. So how can we characterize sets given by constraints like C of x less than or equal to 0, where C is one of these functions that I've been playing with. So we want to compute whether a given box X lies completely inside or completely outside this set. So I forgot to say, please do interrupt with questions at any time. Just call out. I can't see whether you have your hands up or anything. Okay, so we're going to use the constraint programming paradigm, which many people have contributed to. Sort of was crystallized maybe by Luc Jeanlin and I'm blanking on the other person's name. Sorry, in 2009, and so basically we're going to use interval. Naively, what we can do is use interval arithmetic. So if we have a constraint defined by x squared plus y squared is less than or equal to 1, this unit disk, then we can, if we define these interval boxes in 2 dimensions, we want to know is, be able to prove that the green one is totally inside, the pink one is totally outside, and this orange one is partially inside and partially outside this set. And so interval arithmetic will enable you to say that guarantee that all of the points in this box are totally inside the set. And just by putting in the set to this function and computing whether it lies totally inside the interval corresponding to the constraint that we're interested in. So in this case, we're interested in this x squared plus y squared being less than or equal to 1. And so we can just take these intervals and plug them in, the interval boxes, and plug them into this, we'll take y1 and plug it into this C, just like I just did. And the fact that the output is completely inside the interval from -infinity to 0 proves that the box is completely inside the constraint. But then what happens, for this box, for example, when we do that computation, we have a problem because it's partially inside and partially outside, and so the results should be sort of true and false at the same time. And so we do not allow, many packages allow this sort of true and false, or they give a result between the interval from 0 to 1. But the way Julia works, we can't really do that because, so there's actually been a big discussion about this within our sort of community of people that use the package, how exactly we should treat, for example, less than. So if you look at the standard, the IEEE 1788 standard for interval arithmetic packages, which we're still not quite compliant with, unfortunately, but we've been working hard for a long time to be compliant with the standard, but we're not quite there. It does not define what less than means for 2 intervals. Because it's sort of, it has this 3-valued logic. It can either be everything is less than, everything is bigger than, or some is less than and some is bigger than it. And instead of that, it defines these Allen operators for how much do the 2 intervals overlap, basically. But but it's useful to be able to write things like this. So C of an interval is less than 0 if everything is, it's uncontroversial if, in some sense, if everything is less than 0 inside the interval, perhaps. Anyway, so there's a big discussion about that, and there's actually a rewrite of the package right now to allow different flavors and different ways of treating less than, and that's being done by Benoit Richard, who is just turned up and started contributing to the package a couple of years ago and has done a very nice work there. Okay, so what can we do with partially overlapping boxes? We want to cut a box into pieces, a piece that's inside, a piece that's outside, and a piece that's on the boundary. And we're going to do that by using constraint propagation, using the forward-backward contractor, also called HC4. So many people, I guess, in the community know about this, but for those who don't, I just want to talk about it a bit. It's a very beautiful idea. So yes, we have this declarative expression of a constraint. X squared plus y squared is less than or equal to 1. That just declares that I'm interested in that set defined by that expression. And we want to convert that into an algorithm, which actually computes for a given input box, as I said, let's say which part of the box. It removes pieces that I can guarantee lie outside the set defined by the constraint, basically. And the way that we're going to do that is by treating this expression, thinking of it really in terms of relations, and splitting up the expression x squared plus y squared into the smallest possible pieces and treat each of those pieces as relations. So what do I mean by that? So here's, so I'm going to take this same example, x squared plus y squared. So here's the tree, the computational graph, or the AST, or it has different names, abstract syntax tree of this expression. So this is where the computer science comes in. We have an expression defined like defined in this way algebraically, but that corresponds to a sequence of operations in a particular order. So I'm going to first take x and square it, and then take y and square it, and those produce intermediate results, which I'm going to give a name to. So let's say A equals x squared plus x squared, that's this node. B is y squared, that's this node. And then C is A plus B. And so that's, the computer, Julia, is automatically going to do that kind of splitting up of this expression when it evaluates something like this using operator overloading. So what we want to do is an operation on this graph where we, instead of thinking of y equals x squared as just that x is the input and y is the output, so as a function, instead of that, we want to think of it as a relation. So basically, we want to think of the graph of this function, so the set of points x, comma, y, which satisfy this relation. And then we want to actually be able to go forward to calculate y from x, but also backwards to calculate x from y. So if y is a set, we want to know which x's are possible values such that x squared lies inside that set y. And that's what this algorithm is going to do. Excuse me. So this was, I guess, this began at the end of the 80s and was developed at the end of the 90s into this algorithm, HC4. Okay, so for example, A equals x squared. Going forwards, we have some function sqr that takes an interval and squares it. And going backwards, what can we do? We have this sort of reverse version of the squaring function. So you can think of this as a reverse. It's sort of like the inverse function, but it's a set inverse. So we have as an input set A, and we take this square rev, and we get an output, which is another set, which contains all of the points whose square lies inside A. And then if we already had a value for x, we want to intersect the result with the previous value for x to get the new value of x, which are the values, the numbers which satisfy that they're in the original, that satisfy this relation, basically. So for example, C equals A plus B has this reverse function, let's say, or reverse relation, converse relation, A prime equals A intersect C minus B, and B prime is B intersect C minus A, just by undoing this plus operation. So as an example, let's take this x squared plus y squared less than or equal to 1. So how can we actually carry out the computation? We're going to start with two intervals from minus infinity to infinity. And as I said, we'll introduce these new variables A, B, and C as we go up the tree in the forwards pass. At the top of the tree, then, what we have is C is A plus B, that's x squared plus y squared. That's what we're interested in. And we want it to be less than or equal to 1. So we'll impose this constraint that, so here's the less than or equal to 1 is just that the values of C have to lie inside this interval minus infinity to 1. And so the possible values of C are the possible values of C that I computed intersect this constraint. And now I'm at the top of this graph that I drew, and I want to propagate that information back down the tree. So so here's my A. And so I want to take the fact that I've now got a smaller set for C and propagate that back down to A. So, so I do that with this reverse pass that I've just been talking about by inverting this A plus B. Given that C is A plus B, that means that A is C minus B. So here's C minus B, and I have to intersect that with the old values of A. So basically what I'm doing here is splitting up. So this is a relation, a subset of R2 of the two-dimensional plane. What I'm sort of doing is saying, okay, so I'm interested in the set of pairs xy such that x squared plus y squared is less than or equal to 1. And I'm decomposing that by saying, oh, it's the set of xy such that A is x squared and A plus y squared is less than or equal to 1. And I actually have to add a new variable A into my set. So I'm actually, it's very strange. I'm actually sort of trying to solve a problem in a higher number of dimensions in order to solve the original problem. And so I'm actually going to solve a problem in 5 dimensions: A equals x squared, and B equals y squared, and C equals A plus B, and A plus B, and C is less than or equal to 1. So I'm going to solve that problem by splitting, sort of by pairwise looking at these relations and doing these inverse operations. And so people have studied this in a lot of detail. So that was a very nice paper in 2005 by Schichel and I'm really not struggling with names, Neumeier, on how to do this correctly if you don't just have a tree like I have, but actually a DAG, so a directed acyclic graph, where you can reuse basically. So if you have something like sort of, suppose I had, instead of this tree, I had something like x plus 1 squared plus y plus x plus 1, and I'm actually repeating this x plus 1. And so if I do the tree of that expression, I get something like this. And you can see that this x plus 1 is repeated here and here. So instead of that, I actually want to do a DAG. Let's see if this is a package I wrote to just visualize this tree. I want to do the DAG using common subexpression elimination on this tree. And you can see that now I only have one copy of the x plus 1, and I'm reusing it in 2 different places. So that is actually taken account of in our package. In my package. Okay, so yeah, right. So we go forwards, as I was saying, and then back along each node, we're going to do these inverse operations, reverse operations, and the result gives me the box from -1 to 1 all squared. So I started off from the whole plane, and in 10 steps, I compressed the set down to -1 to 1 all squared. So I proved that everything outside this box does not satisfy the constraint using this algorithm. Of course, this is one of the best cases that you can do this, x squared plus y squared less than or equal to 1. If you do something more complicated, you don't get such good sort of compression of the input. Okay, so what we want to be able to do is not write this by hand. Of course, we want to automate this, right? There's an algorithm. I just did an algorithm sort of based on the structure of the input set. So let's automate that. So this is usually done by building a graph or a DAG in memory. And then basically what we end up doing is actually interpreting the expression. So we literally have to build an interpreter, thought of in terms of computer science, where we sort of jump along the tree and look at what is the operation that's happening at a particular node in the tree, and then based on that, call a function and do something and store the result back in the tree. And that is easy, relatively easy to write and very flexible, actually. That's what you need if you want to do something pretty complicated on this tree, where you can go forward and backward on the subpart of the tree, and then based on what happens there, you do something else on the other part of the tree. So it's nice and flexible. But on the flip side, it's slower because you're doing this interpreting. You're looking everything up in the moment. Is this a plus? Oh, in that case, I need to call that function. So instead, our approach is to use code generation. So we're basically replacing this interpreted step with a compilation step. That's why I said that it's basically sort of very standard computer science topic, which I had to learn about. So basically, we want to write a little compiler instead of an interpreter. So instead of building a graph in memory, we're just going to construct a straight line function by defining, just like I did here, by introducing these variables, excuse me, and compile this down. So when I first described this at a SCAN meeting a few years ago to a colleague, they said, no, that's totally the wrong way to do it. You should just build up this graph. But it turns out that actually this is a great solution. This writing out this code automatically is a great solution when you start to think about doing this on a GPU in particular. Okay, so I have this package reversepropagation.jl that does this construction of this code automatically, and it uses the symbolics.jl package to analyze the symbolic expressions and rewrite them. And then interval contractors.jl contains the implementation of these reverse functions that are actually specified that in the IEEE 1788 standard, it is specified that any interval arithmetic package should provide these operators. And they're actually pretty annoying to write and pretty tricky to write, and we still have a few problems with those. We do run the ITF 1788 test suite that was written by, I believe, Nehemiah, and then further developed by, oh goodness, I should have written these names down. Oliver, sorry, I forget the name. Okay, and so as I said, this produces straight line Julia code, just like I was writing by hand up here. So here's an example. I feed it the expression x squared plus y squared and the set of variables x, y. And there's inside this reverse propagation package, this is actually producing, this is actually a Julia code object. This is an object in Julia representing Julia code. This is one of the great features about Julia, is that it has this kind of meta programming ability where you can write Julia code inside in Julia itself. So basically, if I do something like this, my x equals this colon operator produces a Julia code object. So if I do sort of x plus y, that's just an unevaluated expression, x plus y, and then I can reach inside my x. It has a field called args, which are these objects. And then if I just modify the first object to be times, now I have my x is now has changed to x times y. And so that's how we can actually do meta programming in Julia, and how we can take an input expression and rewrite it to an output expression. And then once we have this new code object, we can evaluate it in various different ways. That's a subtle subject as well. And so, for example, here I'm producing this piece of Julia code that is basically what I just wrote by hand. It's calling this reverse function. So reverse of plus calls the sort of plus rev function that's defined in interval contractors. And then I can compile that down to a function. So there's a So if I call forward-backward contractor instead of forward-backward expression, that already does this compilation step. And so I feed in this symbolic expression and I get back a true Julia function, an anonymous Julia function that I'm calling C. And so if I feed in my interval box Y3, that was the one that, I believe the one that partially overlaps, yes, Y3 is the one that partially overlaps. I feed that in and it's going to contract it down by removing the part of the box that is not inside the set. And indeed, when I call Y3, sorry, that was a picture of it here. When I call this contractor on Y3 and I contract it with respect to this constraint minus infinity to 1, I get this purple box. So it's removed the green part. Okay. And yeah, so what is C? It's a function that's basically just a piece of machine code now, because it compiled this set of expressions right down to machine code. And so, as I said, this is basically sort of the fastest possible contractor algorithm you can have, because it's just a compiled straight line function. Okay. So to finish off the computation, we also need to characterize which part of this box is inside the set. And so the way we do that is with separators. These were introduced by Jolin and Desrochers in 2014. So it's basically just a contractor for the outside and a contractor for the inside together. And there are various neat tricks you can do with regards to how do you actually compute those in the most efficient way. And it's not completely clear to me what the best way to do that is. Anyway, I'm going to skip over the details, but basically this is what happens. So here we've proved that the green set is completely inside and the pink set is completely outside. And then this sort of intersection of those two boxes is the piece that has not been, that cannot be proved to be inside or outside. Is basically on the boundary. And so that is how we can compute what with regards to one constraint. And if we have several constraints, then the simplest thing to do is to take the intersection of separators, and then we can actually characterize what is inside and what is outside the set. Okay, so then so that basically kind of solves the problem of constraint satisfaction. And now we can try and apply that to optimization. So how can we do global optimization is well known. For example, the Morse-Gelbo algorithm. So I've got a little visualization of that here. So this is a visualization produced, again, directly from some input function. So here I'm choosing this input function, x times sine of x, and I'm going to do a visualization of the algorithm, this global optimization algorithm running on this input function. So this is the Morse-Gelbo algorithm to find the global minimum, the global unconstrained minimum of this one-dimensional function. So what we're going to do is use an input box, an input vector, an input interval, which I'm representing on the x-axis, and on the y-axis is the output of the interval arithmetic calculation of this function. So you can see that we're overestimating the range of this function by this much, as is usual with interval arithmetic. And then we're going to take the midpoint of this box and evaluate the function there, and that will provide an upper bound for the global minimum. So this green horizontal dashed line is an upper bound of the global minimum. And then I'm going to start bisecting. So let's bisect that box, and the red interval, the red box is what I'm looking at right now. So I'm going to apply the same thing again. So I'm going to look at the midpoint and apply the function. I found a lower value, so I'm going to move the green dashed line down, meaning that I found a better estimate of the lower bound, a better upper bound on the global minimum. And we're going to keep on doing that algorithm again and again, bisecting and evaluating the midpoint until we find a box like this, where the interval arithmetic evaluation of the input set lies totally above the current global minimum, the current upper bound of the global minimum, and hence we know that the global minimum cannot be in that set until we remove it. And we keep on doing that and go along, and we see that we get this sort of cluster of boxes accumulating around the minima of the local minima of this function. But it turns out that actually there's a little bit of the function over here which is lower than those local minima. So once we realize that and we decrease the upper bound below those local minima, then we just kind of go and clear up all those boxes and delete them. And we find that the true global minimum. So that is the more scalable algorithm in action for unconstrained optimization. And so we can, if we just change this function, we actually get a visualization of the algorithm running on a different function. So I haven't tried this, but it should work. So there's the problem is that then you end up with the wrong range, the wrong output range. So I don't know, let's try this or something. Yeah, okay. Anyway, you can see that the point is that in principle, you can just sort of get your own custom visualization. So I've spent a lot of time in my career teaching. I'm very, I think teaching is key, super important. And I love developing these kind of visualizations. And this kind of thing can easily be taught once you have an interactive tool with good visualization and it's easy to use, etc. Can easily be taught as, in the first semester of a university degree in mathematics or whatever subject, and I believe should be. Okay, so how easy is it to write this algorithm? The visualization is harder to write, but the algorithm is just this little piece of code. I guess many people here know that, but the point, one of the points here is that this is a little piece of Julia code, which is the entire implementation of the algorithm, and it's just sort of 20 lines long. And this is generic in the sense that it works either with an input in one dimension or in several dimensions. And that depends on the type of this object. And depending on the type of that object, whether it's just an interval or an interval box, Julia will compile specialized or sort of two-dimensional box versus a three-dimensional box, which are different types. Julia will compile a specialized version of the function for that particular dimension. So here are some examples. So here's an example in one dimension, here's an example in two dimensions, and we found the collection of boxes that contain the global minima and the box that contains the value of the height of the global minimum. Of course, if we wanted to be more precise, we would have to go and do something more clever to then refine this collection of boxes, which we could do. Okay, so then how do we do inequality constrained optimization? We now have to combine these two things together, and that's what I showed right at the start of the talk. So one of the ways of doing that would be to characterize the feasibility of each box using a separator. And then just sort of put that into this algorithm. So in this algorithm, we're evaluating at the midpoint to see whether we can push down this global minimum. And now we have to make sure that we only do that when the whole box is feasible. In other words, is in the intersection of these constraints that we're imposing, and we can do that using separators. So I have been working on how to improve the algorithm to not just use this intersection of separators, but to do something a bit more clever. Okay, and finally, I'd like to talk a bit about GPUs. As I said, so do I have until the half hour? Is that?
Just go ahead. You have plenty of time.
Okay, so how can we implement interval methods in general on the GPU? And so the nice thing about, so what is a GPU? A graphics processing unit is a highly parallel processor. For example, the NVIDIA V100 that I've been using, courtesy of Julia Computing, has about 5,000 mini processors, mini cores. Excuse me. And so you would hope that we would be able to run our computation 5,000 times faster. Of course, that's not quite true because these cores are not so sophisticated as the CPU cores that we usually work with. But we definitely should expect a very big speed up from if we are able to convert our algorithm and run it on the GPU. So how can we actually do that? And my goal is to not have to rewrite, to rewrite the minimum amount of code necessary. So GPUs have been around for, in scientific computing have been around for, say, 15 years or even 25 years. But they've been, usually they've been just really difficult to use because you have to rewrite your whole code. And firstly, you have to rethink your algorithm to be a parallel algorithm, which is already difficult. And then you actually need to code that up. And so how can I avoid doing that as much as possible? You want to have a tool which will do the heavy lifting for you. And so Julia has a set of GPU packages which allow us to do this. So I'm going to try and do some amount of interactive demonstration of this. So I have a terminal to a machine with a GPU, remote machine. So what can we do? So I've already loaded up the packages. In particular, the GPU package is called CUDA.jl, or at least there's a package for NVIDIA cards, and now recently there's been big progress with packages for AMD GPUs as well. So I'm just going to show the CUDA NVIDIA one. So this is for NVIDIA GPU cards. Okay, so what can we do? So suppose I have an interval box like this. So again, how do I make that? X equals interval box of -10. Sorry, need to slow down and stop being so nervous. -10 to 10 in 2 dimensions, and that produces this interval box. And so let's split that up actually. So let's mince that into 10 pieces, and I'll just call the result of V for a vector. So this is okay, it's not, sorry, that's in 2 dimensions, so it minced it into 100 pieces. Okay, let's start with 1 dimension. So let's just do an interval in 1 dimension and then mince that into 10 pieces. So suppose I have a Julia function like f of x is x squared minus 2. Then what do I want to do? I want to, if I want to, for example, find roots of this function, that's conceptually, kind of easier than global optimization or constraint programming. I just want to find roots. I want to find where this function is 0. Then I want to apply this function to each of these boxes or each of these intervals. So the syntax for doing that in Julia is just f dot of v. So for any function f, you can apply it element by element to an iterable object using this dot syntax. So it's like a map. F dot of v will just apply this element-wise to the vector. So we're doing interval arithmetic because I have intervals in, so it will, it automatically detects I'm using intervals, and so it will apply the interval versions of those operators and will give me guaranteed enclosures of the range of the function over each box. Okay, and so then what we need to do is to check which of those boxes have zeros inside. So how can I do that? Well, I can say is 0 in f dot of v. And I want to do that, but I want to check if 0 is in each of those. And so I can actually do dot in. So that's vectorized in for each of those boxes. And that will give me a 0 when it's not inside and a 1 when it is inside. So it's represented as a bit vector, just literally bits 0 and 1. And then I can take the output and so if I call this sort of images f dot of v, so I'm asking is 0 in these images, and then I can choose the subset of images where 0 is inside using this this sort of selection syntax. And so those are I've done this sort of root finding calculation using interval arithmetic. I've excluded all of the places where I have proved that I do not have a root. So now how can I do this on the GPU? This seems like the exact kind of thing that I should be able to do nicely on a GPU. So what the first thing I need to do is actually move my vector over to the GPU. So let's call VV the GPU copy of this input vector. So I do that with this coup-array of V that will copy this whole vector over to the GPU. Of course, that's not really, you don't really want to do that, and it's a bad idea to copy a lot of data over. So this is just an illustration. You would probably just copy a single interval and then sort of split it up once you're on the GPU, but just an illustration. Let's do it like this. And then what do I want to do? I actually want to run this function f on this set of intervals that lives on the GPU. I just realized that this is not going to work. Well, let's try it. So what I would like to write is this, f dot of VB. So what Julia is going to do is take this standard Julia function and try to compile it to a version that runs on the GPU. And that's exactly what just happened. And so the only thing, I didn't do anything. I did no GPU programming whatsoever. Somebody else did the hard work for me. Tim Bezar, who's now at Julia Computing, which is this company that supports the development of Julia and employs the core Julia developers who develop the language, and Valentin Churabi, who's my collaborator at the Julia Lab in the group of Alan Edelman. They really, and various other people, of course, wrote this amazing suite of packages. So basically what's happening here is that Julia takes this f function, that I defined, like this. And so, for example, suppose I pass in f of 1, what is actually Julia doing? Well, it's firstly doing type inference. So I'm passing in an integer, and here is basically we're seeing a sort of what's called SSA form. So we're seeing a sequence of definitions of new variables called %1 and %2, and it realizes, so let's do false. So you can see that here, basically, it did what I did with this syntax tree, which is just sort of linearize, flatten the syntax tree into just a sequence of variable definitions. So as I said, this %1s are the new variables. You can see that it's just sort of writing out the sequence of operations x squared minus 2. So here's a 2, and then I take 2 to power, and then I subtract 2. And it's doing this type inference as well. So it knows that since I'm passing in an integer, at each step, it knows that the result is an integer. This is all automatic. And then at the next step, it realizes that, oh, I'm taking a power of an interval. That means I need to call this particular function. So in fact, because it's squaring an integer, it knows that the efficient way to do that is just multiply these two integers together. And then, so the next thing it does is actually turn this into LLVM code. So LLVM is this intermediate representation that most compilers today use to compile to machine code. So if you can generate LLVM, then you've done sort of the hardware, or let's say the compiler does the hard work of converting that into machine code for your particular machine. So here's some, very kind of low-level representation of this code. And then the final step is that LLVM compiles that down to actual native machine code. And so you can also examine the output of the machine code. So you can really see the whole process of compilation. You have introspection into exactly what Julia is trying to do. Or, so if you have sort of performance issues, then you should be able to see that by looking at this stuff. And so in particular, this LLVM step is interesting because of the following. So suppose I make an interval type with an a sort of low, which is a float 64, and a high, which is a float 64, and then I define how to add two of these things together. So x, which is a my interval, and y, which is a my interval, is going to be a my interval of x dot low plus y dot low and x dot high plus y dot high. Now I just make two of these things. So x interval mindful of 1 and 2, and y is mindful of 3 and 4. And now I just add these together and I get mindful, the correct mindful. So let's look at the code that is generating. So at code types of this thing, it's actually, you see, completely removing from the calculation. It has just kind of removed, well, no, it hasn't quite removed it yet. This abstraction, which is this my interval object. So what I'm trying to say is Julia allows us to have zero cost abstractions. So once we get to LLVM code, basically you can sort of see if it's difficult to read this stuff, but basically it's just doing, just moving around data in memory. There's no trace left of the fact that I have this my interval type going on. And so what the GPU packages do is take this LLVM level where we've got rid of all of this Julia sort of high level stuff, and it's just reduced it down to these computations. And now it takes that and converts those into the equivalent thing for the GPU. And then NVIDIA's compiler will convert that into the actual machine code that is going to run on the GPU. So PTX, I believe, is the name of this sort of intermediate level code on the GPU. This is the equivalent to this. And so that's what is happening inside these packages. And when I do this broadcast on, I had this array that lives on the GPU. That's because it's a Q array. It's just a new type of array. And broadcasting works. So the point is that what's happening here is that this syntax is converted into some function call to a broadcasting operation, and it's specialized on Q arrays to do this whole operation that I was just talking about. So convert the function to a GPU version and then run that function element by element on this code. And that's all automatic, developed, as I said, in this package. Okay. And so now the difficulty is, well, now what do I need to do? I actually need to do the same thing. I need to choose which elements in this vector contain 0 or do not contain 0. So I could try and do the same thing again. 0 dot in this. That's actually going to work. That's fine. So what just happened? It compiled on the GPU, a special version of this function in and broadcast, etc., that worked on the GPU. And now the problem is I need to actually choose which elements of this array are or not 0 in this array. So that's actually a tricky thing to do in parallel, but we managed to solve that problem in a way that I don't particularly want to go into right now. But so you can actually write now. So again, images2 is f.vv, and I can write the same thing that I wrote before. Images2, I'm going to select the places where 0 is piecewise, is element-wise in images2. And that actually all works. So briefly, what it does is it actually has to work out which threads or which processes, which cores basically need to return. Each core is going to calculate a 0 or a 1, and then each core needs to decide if it should be in its computation should be in the answer or not. And that's some kind of reduce operation or something like that, an accumulate operation. And so what we actually ended up doing was take the cum sum of this vector. So if I do cum sum, that's the cumulative sum of this vector, you can see that it's telling me which it assigns distinct numbers to each core that is actually going to return a response, basically. And then I collect those, and that that is all hidden in this selection operator. Okay. So one little wrinkle is what happens in my original function f. So I have this vector VV, what happens if I define a new function G, which contains something like cosine in? Is that going to work? In order for that to work, well, when I say cosine, what am I actually doing? Well, cosine of a floating point number on my CPU calls a particular version of the cosine function, which is actually very interesting. So let's just have a quick look at that. So if I do @edit of cosine of 0.5, okay, no. Let me do that locally instead. This opened my editor to the source code of Julia. And you can see the definition of the cosine function. So cosine in Julia is actually written totally in Julia since a couple of years ago. So it used to call into some C math library like glibc, libm. But a couple of years ago, all of these, or most of these elementary functions were rewritten totally in Julia. So you can see that what does cos do for an x of type t, where t is either float 32 or float 64, single or double precision, it basically checks if x is small enough, then it's just going to call straight through to this cos kernel function, and that's just down here. So cos kernel of y, which is a float 64, is exactly this piece of code. So you can see that it's basically calculating a polynomial. This @Horner is a macro that calculates a polynomial evaluates a polynomial using Horner's method with these constants, DC1, etc., which are right here. So this is basically the result of doing some kind of Remez algorithm on cosine in this particular interval from -π/4 to π/4. And you see that, I mean, this is the most readable implementation of cosine that exists anywhere, I think, because apart from anything else, just because we can use these Unicode symbols to define variables in Julia. And the point is, you can actually go and see what it's doing, and there are experts on this call on such things, and they can say, oh, that's a terrible implementation of cosine, I can do better. And then you can just go and contribute that straight back. Okay, but the amazing thing is, you have this visibility right into exactly what is going on inside your computation. Okay, so now if I call cosine on a float 64, it's doing exactly this computation. But now if I am working on the GPU, what version of cosine should I use? And so this was a problem for a long time, but recently it's been fixed. And so basically what you want to do is sort of automatically go inside the code. So I'm calling code here, which contains a cosine. You want to go inside and replace the cosine, the abstract Julia cosine function, with a call to the particular version of cosine that works best on the GPU, which is NVIDIA's optimized implementation of cosine that they provide. And so that is now happening automatically when I do this operation. Okay. And so finally, how do I do constraint propagation on the GPU? So this is what is not unfortunately working. Sorry about that, but it almost works. So I need to, so I have some expression like x squared plus y squared. I call my forward-backward contractor. That produces a Julia function that's just literally a straight line piece of code that I showed before. And now what should I be able to do? So if I have a constraint like 0, 1, and I want to basically evaluate, so I have my vector V, which lives on the CPU, I should be able to broadcast this function which does the constraint propagation on my vector V, and I need this slightly strange notation, ref of constraint to, okay, no, so I need interval boxes now. So let's do W, which is interval box of, let's say minus 10 to 10 in 2 dimensions. And I'm going to mince that into, 3 pieces. Okay, so there are some boxes, let's say 4 pieces. There are some boxes, and some of them contain 0 and some of them don't. And so now I'm interested in doing this contraction on those boxes. So I should be able to do C of W ref constraint. And so that should apply my contractor element by element to W, contracting it according to this constraint. So the output of, I wanted the output to be in 0 to 1. And so you can see that most of these boxes get contracted away to the empty set. And then some of them don't, and they get contracted down to whatever they get contracted down to. So this is what I want to run on the GPU. And so if I copy over this box, this set of boxes to the GPU. By the way, this is already, just doing this copying operation is already amazing, because what I get is, interpreted to me as a set of interval boxes that live on the GPU. Of course, what is actually happening is that that's just a set of floating point numbers that are in some array that live on the GPU. But Julia is interpreting that as if it were an array of interval boxes, and it's allowing me to call all of my functions that work in interval arithmetic and use all of this implementation of interval arithmetic straight on the GPU without me doing anything at all. I forgot to even talk about that amazing aspect of it. So, if I do just sort of write some function f that takes in a pair xy and just does, I don't know, x plus y, let's say, then I can broadcast this on my vector of interval boxes that lives on the GPU, and it works. So this is already just a miracle, magic, as Arthur C. Clarke said, any technology that is sufficiently advanced is indistinguishable from magic. This is basically magic. The fact that I can do these interval operations on the GPU. And so now the interval operations that I want to do is the sequence of operations that does this contractor. And so finally, I want to do C applied to W with this constraint, with this ref, just means prevent my broadcasting from acting on each of the elements in here. And this is what fails. So we're almost there, but there's just some very strange thing going on. This has worked in the past, but versions of things have got changed, and so I just couldn't quite get this all to work. I'm not quite sure what's going on, but it basically is there. So we can basically run interval constraint propagation on the GPU. Why? Because we ended up doing this code generation approach to it instead of building a tree in memory. So building a tree in memory is terrible on a GPU, but doing straight line code is perfect for running on the GPU. Okay, so that's the end of my talk. So yeah, as I've tried to show, we have a fast implementation of constraint propagation, interval constraint propagation in pure Julia, with an easy to use symbolic interface to build up your expression that you can then convert into a contractor easily. And I'd love to hear if anybody has suggestions for where to take this. Okay, thanks very much for your attention.
Okay, many thanks, David, for a very interesting presentation. And yes, also thank you very much for this live demo that you tried. And now, is there anyone who has some questions that you want to ask? Okay, there's at the moment no one who has raised their hand. Maybe let me start with some questions. First of all, I was wondering concerning the performance, some kind of performance overhead that you have to pay when you're using Julia to perform GPU computations. Right. How much is this more costly than, for example, directly writing some CUDA code and run it directly on the GPU? For example, if you just use, I think there are some basic built-in functionalities from the Boost library of interval arithmetic that are directly included in the CUDA library. Did you make some comparison?
No, I haven't done any comparisons like that. I'd be very interested to do that. I think that I believe that it should be just basically as the same speed. Maybe. Yeah, good question. That's a very good question. I didn't realize that there were these other options. Yeah, so as I said, you are basically you're compiling your interval library straight to the GPU, and so you basically have a one-to-one, pretty much a one-to-one version of whatever you wrote in Julia on the GPU. And so it sort of depends how good your interval library is to start with on that you wrote in Julia on the CPU, how good that is should so if we wrote exactly the same as the boost library in Julia, I believe it should be compiled down to exactly the same machine code in the end. So one thing I do have to say is that whenever you're using Julia, you probably saw that there's a lag because it is compiling, right? So when I run one of these not that particular one, but like this f dot, the f dot of WW, the first time I ran it, there was a big delay because it had to do this huge compilation step. But then the second time I run it, it realizes that it already compiled the function, and so it's blazingly fast. So how fast is it? For root finding, it's without optimizing the algorithm on the GPU at all, to actually sort of do the whole root finding computation with bisection and everything, using the Newton method, or no, Kravchik method. So you can do Kravchik method on the GPU using this. So yeah, maybe I should just show that quickly. So there's this forward diff library for forward mode automatic differentiation. So you can do sort of, if you have a function f, like I have, then you can do forward diff dot gradient of f at the input value 3, 4. Okay, I have to use another library, static arrays, to get small arrays that are efficient. So I just write S vector of 1, 2, and that gives me a sort of efficient 2-dimensional array. And so if I do forward diff dot gradient of my function f at the position 1, 2, at the vector 1, 2, I get back the gradient. And now I want to broadcast that over all of my vectors, all of my interval boxes, and that didn't work. Yeah, so this is the kind of thing that used to just work, and now it's not working. So yeah, that's a shame. But anyway, in principle, you can just take this pre-existing package that knows nothing about intervals, that knows nothing about GPUs, but because it produces a sort of set of straight line code, you can just, in principle, immediately run it on the GPU, and it will automatically cross-compile everything to the GPU for you. So you don't have to write your own forward diff library and your own interval library on the GPU. That's the idea. That's the goal. And yeah, so I totally agree that the key question is, is it efficient? And I believe the answer is yes, but I haven't done the comparison.
It's because I think there are plenty of applications, for example, where you can exploit this kind of data parallelism. For example, when you want to perform parameter identification for quite complex dynamic systems also.
Right, definitely, yeah.
And so, since you just have shown this forward differentiation here, is this working to an arbitrary order, or is there some kind of upper limit? Let's say only the first derivative, second derivative, or? Yeah,
in this particular package, so Hessians are working well. Beyond that, this is not really the right package to use. So we wrote a Taylor series package, but that uses, so that's something I have to say, that not any Julia code will compile to the GPU. So for example, the Taylor series package uses arrays, like standard Julia arrays, and the standard Julia arrays are mutable, so you can add an element to an array, and so that makes it, it's a complicated data structure, and that is not suitable for the GPUs. That's why I use these S vectors. So what we would need is a version of Taylor series that worked, that basically was parameterized by the dimension of the number of derivatives you wanted, or something like that. And I did actually start to write a package like that, static Taylor series. And so once you have that package, then you should be able to do, you could even do Taylor models. So we have also a package for Taylor models, but you have to make sure everything's static in this sense that you have this sort of, ahead of time exactly the size of all of your objects, basically. Once you have that constraint satisfied, then you can do it all on the GPU. So we should be able to do Taylor models on the GPU, and all of this stuff that this community has developed it's just engineering, and it's a lot of work. It's basically been two of us doing most of this stuff, so we haven't been able to do everything that we would like. But yeah.
Okay, and that means if the Taylor series expansion is working, for example, one could also compute Lie derivatives efficiently. And
yeah,
I think since I've seen before that Bernd is in the audience here, and he had given, I think it was 1 year ago, almost exactly 1 year ago, a talk on using interval methods for proving observability of dynamic systems. I think this would be right away one possible application.
Yeah, no, I definitely, there are lots of applications. There's just some, annoying engineering to get there.
Okay, now is there anyone else who wants to ask a question? Don't.
Andreas?
Yes, Bernd?
Yeah, you just commented on on this joint work with Thomas on observability, and I think it's a very nice idea to couple that with the ideas from this talk. That would be, we implemented everything in MATLAB using the IntLab toolbox, and then had to do everything by our own, by section and so on and so on. And so Thomas, sadly enough, had already left the university. He now works with DSpace on MATLAB implementations on signal processors, and but he is still interested in collaboration. So I will,
yeah, great.
I will direct him to the copy of this talk, and we look forward to use some of your ideas, maybe to improve our algorithms. We had some experience with CUDA programming with respect to some other industry projects where we use CUDA hardware or NVIDIA hardware for optimization only with local methods, but very, very fast using that hardware. And then we could do we could reduce the speckle errors in some laser measurement techniques, and that was a completely different application where we had no objective function given as a function, but as a measurement made on an experimental setup. And so every function evaluation was very, very precious and costly, and so but we had good results with that, and so we had some experience with CUDA, and it's but when you do it by hand, not by a professor, you have to proceed to in some sense relearn programming.
Yeah, exactly.
Because
totally, yeah. Right, so that's what I mean, I have tried to do that in the past, and actually, so one of the things I forgot to mention is that I mean, I showed the magic side of using Julia, but of course, not everything you want to do can just be done by broadcasting a predefined function. So you actually can write your own kernels, your own GPU kernels in Julia. So you write Julia code, and then you specify, this piece of the program is a GPU kernel, and it will compile that to CUDA. And so even if you need to write things by hand on the GPU, this is still a sort of great option for actually doing it, because you're using a sensible programming language instead of this weird CUDA thing.
Yeah. Okay, but nevertheless, thank you very much for this interesting talk.
Yeah, sure. Thanks.
I will look into the literature and also the copy Andreas will send around. I think in YouTube, du stellst das bei YouTube zur Verfügung.
Yes, yes, this will be definitely put on YouTube again.
It's sad that my PhD students had no time to attend us, because they all are in oral examinations as Beisitzer, and so they are not able to watch your talk. But I will direct them also to this talk. Thank you very much again. Yeah. And Andreas, I have to leave now, but thank you very much for organizing the seminar. And I think it was nearly exactly 1 year ago that when Thomas.
I think it was beginning of February.
Yeah, genau. Okay, thank you very much.
Okay, then see you soon, Bernd.
Bye.
Okay, but maybe I'd like to add some further idea, because I've also seen that Lorenz Skillner is here in the audience, and I was it was also around 1.5 years ago, I was supervising or co-supervisor of his bachelor thesis. And now Lorenz is working towards his master diploma, and he will continue afterwards also as a PhD student. And I know that he already started to make first comparisons between intervals in Julia, evaluated on the GPU, and also he made some comparisons with CUDA. Maybe Lorenz, do you want to comment a little bit?
Yes.
Yeah, I'm very interested
First
to
of
hear.
all, thank you for your talk.
Thanks.
I don't know, maybe you remember my question from the Julia discourse concerning also global optimization.
Oh, right.
No, it's yeah, I was about to ask you something about it, but
okay.
I just saw in your demonstration that you encountered the same errors as I did.
Okay.
So you said it used to work, but now it doesn't.
Yeah.
Specifically the forward diff gradient.
Right. Yeah. I've definitely done that before. Yeah. So yes, right at this moment I can't see what the problem is. Oh yes, I can. Oh yeah. Yeah. So even on the CPU, it's not going to work actually. I think. That's just a stupid. Yeah. That now is yeah. When you do it on the C, usually you just have to do things on the CPU to see what's actually happening. So it's no method matching gradient of f with an interval box. So you just have to define it. So forward diff dot gradient of f with x, which is an interval box. So I'm defining a new method using f with x dot v. V. So what is so if x is an interval box. So let's say x is the interval box of 0, 1, 2. Then x dot v is this static vector that I was talking about that lives inside x, and that's what we need to take the gradient with respect to. Now it should work. So now I can broadcast forward diff dot gradient over w, and then I should be able to broadcast it over w as well. So that I think that was probably the issue. Yeah. Thanks. Good question. Yeah, there you go. Okay, so that's
thank you.
There we have the gradient working on the GPU, right? And so now we can do, Kravchik method on the GPU that I have had working before, and so we can do proper root binding, and then we can, global optimization is 10 lines. It's basically the code I wrote, but you have to write it in a vectorized way, and then the Morse-Gilbert algorithm on the GPU, and then the difficulty is the contractors. That's what I couldn't get to work still. I'm not really sure quite what's going on, but I have done it before. As I said, it really is pretty, there's a lot of moving parts in this whole process, this compilation chain. So it's difficult to get it all to work together. So still a work in progress.
Yeah, but thank you very much. I will try that out later.
Sure. Yeah, I'm happy to, just write to me in person, and we can have a call or whatever.
Yes, sure.
Okay, that means a great opportunity to resolve one of the questions.
Okay, great.
Do we have anyone else in the audience who wants to ask something
I actually have
to David?
I actually have to be going. I have another.
Okay.
Meeting. Yeah.
Okay,
well,
then.
Thanks so much,
David,
Andreas.
Yes, many thanks again for your presentation.
My pleasure,
and
thanks.
as I already told Bernd before, I'll put the recording of your talk on YouTube. And definitely, if there's anyone else who wants to ask questions, just send an email to David. And yeah, thanks again to all of you to attend this seminar today. And as usual, I wish you a nice Friday, or Friday noon to David, to the rest Friday afternoon, Friday evening, and have a nice weekend. And we'll see each other on Friday in 2 weeks. And our next speaker will be Brenna Rego, who will talk about constraint sonotopes for state estimation and pyramid identification. And from that point of view, see you again soon.